When we talk about linear polarization, we set one condition to get the linear polarization state. The condition is that the phase for the x component and for the y component are the same. And now we want to relax this condition and show you the arbitrary polarization state. And on this page, we first write down the field component along x direction and y direction. And we already know the propagation direction is along z. So this is the plane wave propagating along z with the electric field on the xy plane because this is a transverse electromagnetic wave. So in this expression, we allow the amplitude for the x component and y component to be different. At the same time, we allow the phase for the x component and y component to be different. And the phase difference is denoted by this symbol phi in this red box. And to simplify this expression, we group same expressions into a symbol called psi, which is omega t minus kz plus phi 0. And so we more or less simplify it a little bit and rewrite this expression to be this. Just put this same phase into this psi, and so we stand out this phase difference between these two components. And with some algebra, you can organize all the variables into this expression. And I urge you to do it as an exercise. Basically, you'll get this expression when you divide your x component electric field by the amplitude and take a square of it. And you do the same thing for the y components. And then there's a cross product term for the xy component. And this expression is going to give you a value equal to sine square phi. And again, this phi is the phase difference between the x component and y component. And we want to know how this electric field on the xy plane will change over time and over distance. And I want to bring out one expression you are already familiar with when you study in high school. You deal with this expression, ax squared plus the bxy plus cy squared plus dx plus ey plus f equal to 0. And in high school, you try to figure out if you express this in the xy plane, how this curve would look like. And turn out that you test the value for the coefficients. If you get this b squared minus 4ac less than 0, then you can claim that this expression will give you an ellipse in space on the xy plane. So let's do the same test to this expression. Assume this is just your x squared, x, y, and this is y squared. So in this expression, the a is equal to 1. Basically, this is the coefficient of this term. And b is equal to minus 2 cosine phi, is the minus 2 cosine phi to be the coefficient of this cross product term. And c, again, is equal to 1 because the coefficient for this term is 1. And you just put this ABC into this expression, and turn out that the calculation gives you minus sine square phi. And for sure, this term is going to be less than 0 because you have a square here. So it's always a value less than 0. So this expression, in fact, tells you a trace on the xy plane that is an ellipse. So let's continue the conclusion from the last page. Now we write the electric field to have two components. And in these two components, the amplitude of the x component and y component could be any value. They are just arbitrary. And there's, in general, a phase difference between these two expressions. And we denote this phase difference to be phi. And from the last page, we understand that the electric field, when plotted on this xy plane, is going to be an ellipse. and the trajectory of the this ellipse will coincide with the tip of the electric field over time. So imagine that if you allow this time to start to tick, then the tip of this electric field is going to trace out this ellipse on the xy plane. And also from the theory of the conic expression, you can calculate the slant angle of this ellipse to be this. And this is only related to the amplitude of the electric field along x direction and y direction and the phase difference. So in fact, when we write down this expression, it's just too complicated because there's no role for this omega t minus kz plus phi 0 in this final result. So on the next page, we're going to simplify the expression. Just try to leave out those complicated variables and just keep these three variables, which are the amplitude of the electric field along x direction and along y direction, and then the phase difference. So let's adopt a complex notation. Again, let's write down the real expression, and then just keep the relevant variables ex0, ey0, and also exponential gfi, and drop all the rest of the variables. So this expression is already enough to tell you the polarization state of the wave. And sometimes we express this by using a column vector, and just keep the s component of the amplitude as a first element, and then keep the y component of the electric field as the second element. And we call this the Jones vectors, because in these vectors you already keep the all the relevant parameters. So this is already sufficient to define a polarization state of the wave. And in general, if the ex0 is not equal to ey0, and in general, if you have a phase difference between these two components, then the electric field on the xy plane will trace out an ellipse. And we call this the general, general polarization state for the electromagnetic wave. So we have gone through some general analysis for a polarization state. We allow the amplitude of the x component and y component to be different. We also allow there's a phase difference between these two components. And we found that this polarization state basically will trace out an ellipse on the xy plane, and the tip of the electric field will just rotate about the trajectory of the ellipse over time. And so in general, a polarization state of a TEM wave is going to be a slanted ellipse in the xy plane.